This is a video that is a transitioning kind of topic between section 3.6, the end of chapter 3, and getting into chapter 4. Mostly we're going to focus on section 3.7 in this video, which is about something called the trace-determinant plane. In the Mathematica notebooks, you've been working a lot with the trace and determinant, and some in your written assignments too, to find eigenvalues and eigenvectors and ultimately find the general solutions. I want to motivate this by thinking about something from section 3.6, and that's going to be the harmonic oscillator equation. So I'll write that up on the screen. I'll write it in this form. Is it dark enough? Looks good, okay. Write it in that form. Y double prime plus P right, Y prime plus QY equals 0. You should always remember when you see this, when it's referring to the standard mass on a spring, that P is B over M, it's the damping divided by the mass, and Q is K over M, the spring constant divided by the mass. And all these numbers, these parameters, are positive quantities. Technically, Q has to be bigger than 0 because that's the spring constant, and otherwise you would have no spring. P could be 0, as we saw in the last video about section 3.6, and also including some things in 3.4. In the undamped case, P actually can equal 0. One real quick thing I want to say is that actually harmonic oscillator equations come up in lots of situations beyond just a mass on a spring. A more generalized version comes up when you have a swinging pendulum. But there are lots of other things in physics and chemistry, lots of other oscillators that act like harmonic oscillators. So it really applies to a pretty wide class of problems. All right, let's come back up to the equation. What do I want to do now? What I want to do now is just assume for the sake of simplicity that the P is 1. Excuse me. That Q is 1. And that P is a parameter that I want to, well, think about what happens when I let it vary. Now think about what you've done in the past when you've let parameters vary. You've looked for bifurcations. So we're coming back to bifurcations, which is one of my favorite topics. It's what gets me excited about the subject of differential equations. And that's going to be the focus here. P and Q parameters are constants when we think about any one particular differential equation, but the interesting thing to do with those is to think about what happens as those constants change. So we use another name, we call them parameters, because we look for qualitative changes in solution curves as those constants change. So how would we do this? How do we look for bifurcations here? You might have a guess, thinking that it's related perhaps to the quadratic formula. It is. One thing we could do here is convert this to a system. The capital Y vector dt equaling 0, 1, negative Q, negative P times capital Y, where capital Y is the vector whose components are little y and little v. And we can focus on the trace and determinant of this matrix. Use that formula for the eigenvalues in terms of the trace and determinant. You also know from the previous video and from working on material in section 3.6 that you could just take this second order equation and go right away to the characteristic polynomial and then right from that to the quadratic formula. Either way really is okay. If we do it this way, think about this matrix A. I guess I'm not quite letting Q equal 1 yet, but I will eventually. The trace of this matrix, which we call T for short, TR is the abbreviation for trace, is negative P. And the determinant, capital D, or det of A, is 0 times negative p, 0, minus negative q times 1. In other words, the determinant is q. From this, we could go to the quadratic formula. We could go to the shortcut formula for eigenvalues that looks like this. Plug in how the trace and determinant depend on p and q. The trace is negative p. Trace squared is going to be p squared. Minus 4d is going to be minus 4q over 2. And if you look at this thing, this is what you would have gotten if you applied the quadratic formula essentially to the original second order equation at the top. Although technically you'd be applying it to the auxiliary equation where you replace the primes with powers of an unknown s, or lambda, whatever you want to call it. You would get s squared plus p times s plus q. S to the 0 is like the y. Equaling 0, and the quadratic formula directly applied to that equation would have given you this. We saw last time that p squared minus 4q, written in terms of m, b, and k, can help us decide when our system is an undamped oscillator, in the case when p is 0, or underdamped when p squared minus 4q is less than 0, or critically damped when it equals 0, or overdamped when it's greater than 0. And so a bifurcation occurs when p squared equals 4q. There's a change from underdamped to overdamped. I suppose you could even argue there's a bifurcation at p equals 0 in changing from undamped to underdamped. You can maybe make that argument too. Actually, it's kind of funny. Some people in math might argue that there's essentially no bifurcation at all, because to some mathematicians, a spiral sink is essentially the same as a real non-spiral sink. We are thinking of them as being different. They look different. To us, they're qualitatively different. But to some mathematicians, depending on your point of view, they're both sinks, so they're still essentially the same. Though when p is 0, then you've got a center, and I guess you'd have to say a bifurcation occurs as p increases away from 0. Well, let's come back now to plugging in q equals 1 and focusing on one parameter, p. If we just focus on one parameter, it's a little simpler to think through about where the bifurcation occurs. This bifurcation is depending on p. Let's actually ignore the bifurcation that occurs in a sense at p equals 0, even though it really is there, especially if it allowed negative values of p for some kind of negative damping or something, I suppose. Let's focus on the bifurcation that occurs when p squared minus 4 is 0. That's going to imply p squared is 4, and if I'm only focusing on non-negative values of p, that bifurcation from a underdamped mass on a spring to an overdamped occurs at p equals 2. P equals 2 would be the bifurcation point there. So we can focus on one parameter is what I'm trying to say. And we can even draw a bifurcation diagram in a couple ways. One way we could do it is we could just focus on the parameter p, thinking of that as being on a number line. The bifurcation value is at 2. We could label it like this. In here, between 0 and 2, strictly between 0 and 2, not including the endpoints, we would have the underdamped case, underdamped. The origin would be a spiral sink. That word says underdamped, this says spiral sink. And then when p is strictly greater than 2, then you've got the overdamped case. That would be a non-spiral sink, or real sink. I'll just label that sink, like the book does. That would be one way you could draw a sort of bifurcation diagram. You don't really see it in the same way as we did with chapter 1, because I'm not looking at the dependent variable in this graph. I'm only looking at the parameter. You actually can sort of make this bifurcation diagram more sophisticated, but in doing so, because our system is really two-dimensional, it almost becomes too sophisticated. We have to imagine the bifurcation diagram really three-dimensionally. Let me see if I can draw it. Looking up at the screen here, I'm going to draw a line, and you need to imagine this line three-dimensionally. Imagine it as coming out of the screen at a certain angle. That'll be my parameter axis, my p-axis. In the plane of the screen, I'll draw a little square here that's supposed to represent the plane of the screen, where p is 0. I could draw a qualitative picture of the phase portrait. I guess I am going back now to focusing also on p equals 0 and the bifurcation that occurs there. When p is 0, you've got a center. The origin is a center. The horizontal axis for these mass on spring problems is y, and the vertical axis is v. Imagine those going negatively. This is supposed to be in the plane of the screen. I've got an equilibrium point at the origin, and I've got solutions that lie in ellipses. That's what these are supposed to be. Centered at the origin. When p is a little bit bigger than 0, between 0 and 2, a bifurcation has occurred as p increases past 0. No longer do I have a center, I've got a spiral sink. It'd be nice if I had a different color that showed up well. I'm going to draw another square in here that's supposed to represent a plane that's in front of the screen at some positive value of p less than 2. The origin, let's say, intersects the square there, right there. I didn't make it symmetric. Sorry about that if that's confusing. And the origin will be a spiral sink for that plane and all other planes between 0 and 2. A bifurcation occurs at 2. I'll draw a 2 right here. That's supposed to be p equals 2. I'll draw another square that's supposed to represent another plane at p equals 2. Well, or let me go further here. Draw my picture a bit further. At p equals 2, that's where you're going to have one repeated eigenvalue. And there will be one line of eigenvectors. You'll read about that in section 3.5, which I'm sort of skipping in these videos. There'll be one repeated eigenvalue and one line of eigenvectors. That's the critically damped case. You'll get some solutions going about like this. But when p is bigger than 2, that's overdamped. You'll have two distinct real eigenvalues and two distinct lines of eigenvectors, two distinct lines of straight line solutions, which might look something about like this. Maybe one about like that, and one about like this. It's a sink. Let's say this one over here is the one that it approaches to the origin tangent. Something like this. You gotta really use your imagination when you're looking at this, because it can get confusing. Okay, you got to imagine that p-axis that I drew initially. That's not supposed to be part of the phase portrait. It's just indicating the value of p that this is at. With some value of p bigger than 2 here. The picture gets messy in other ways. The 2 kind of got lost in the shuffle here. That's supposed to be a 2 there, p equals 2. So you've got to look at this kind of picture with the right kind of perspective to understand what it's showing you. And so take a few minutes to really think about it see that it is really, in a sense, giving you a kind of bifurcation diagram. You won't have to draw any of these for your homework. All that is supposed to be motivation for the content of section 3.8, which focuses not necessarily on harmonic oscillators, but in general two-dimensional linear systems. And let's go back to using x's and y's. So I'm going to let y, capital Y vector, be the vector whose components are little x and little y. And I could write a general matrix here times y. I could put an A, B, C, and D. But if I do so, then I have actually 4 parameters to think about. And the parameter space, if you will, would be 4-dimensional. So it'd be nice if we could just focus on 1 or 2 parameters. For our first example here, let's focus on 1 parameter. I'm going to go ahead and, as usual, let the upper left-hand corner of this matrix be an A. But I'm going to fill in some other things in the other entries of this matrix. Some of them could be, or all of them could be constants, like, for example, the lower left entry I'm going to choose to be 1. But others of these still could depend on A, my 1 parameter A. And this particular problem happens to be number 3 in section 3.7. And in that problem, the upper right corner is A squared plus A. That's how the upper right entry depends on the parameter A. And the lower right entry is just an A. The trace and determinant of this are 2A. For the trace, A plus A is 2A. And determinant is going to be A squared minus 1 times A squared plus A minus the quantity A squared plus A, giving us a simplification down to just negative A for the determinant. So we can quickly find the eigenvalues. Trace is 2A plus or minus the square of the trace is 4A squared minus 4D is going to be a plus 4A all over 2. This will simplify to A plus or minus. We can factor the 4 out of the expression under the square root, and the square root of 4 is 2, and we can cancel the 2 at the bottom. And we're just left with the square root of A squared plus A inside, or if you like, you can write that in factored form as A times A plus 1. So what kind of bifurcations are going to occur here? It takes a bit of thinking. Certainly it seems that A equals 0 and A equals negative 1 are possible bifurcation values. Perhaps the only ones. We could draw in an A-axis. And here I'm not putting any restrictions on A. A can be any real number, so I'm not going to say A has to be non-negative here. It seems that 0 and 1 are possible bifurcation points, the values of A that make the thing under the radical equal to 0. Those are indeed bifurcation points, but let's think about it to be careful. What's going to happen with the eigenvalues? That's the key here. Let's focus first when A is between 0 and 1. That'll be between 0 and 1. And A times A plus 1, think about it a little bit. That'll be, you know what, I made a mistake. All right, fix that mistake. Negative 1 and 0. Let's imagine A is between negative 1 and 0. A times A plus 1 in that case will be negative, right? Like if A were negative 1/2, we'd have negative 1/2 times positive 1/2, we get a negative number. So we'd have a negative number in there, negative square root, we get complex eigenvalues. So in here we have complex eigenvalues. Moreover, since A is negative in that range, the real part would come from this here. The real part would be negative. Think about it. That's going to mean you're going to get a spiral sink. This is with negative real part. So we get a spiral sink at the origin. All right, let's think about A positive. A positive, that's positive, plus or minus square root of a positive number. A times A plus 1 is going to be positive. So definitely A plus that square root will be positive. What about A minus that square root? Well, if A is positive, A squared plus A will be bigger than A squared. And therefore, the square root of A squared plus A is going to be bigger than the square root of A squared. Bigger than A when A is positive. So, A minus that square root will be negative. Think about that a bit. You're going to get one positive real eigenvalue and one negative real eigenvalue. I'll just write it quickly like this. Lambda 1 will be positive, lambda 2 will be negative. You'll get a saddle point at the origin. So definitely a bifurcation has occurred as A passes through 0, excuse me. When A is 0, you'll get 0 for both eigenvalues, and that's a 3.5 kind of topic. I won't go into what happens there in this video. Definitely a bifurcation occurs there. You get a repeated eigenvalue of 0 at A equals 0. When A is less than negative 1, for example, negative 2, this product is actually positive. A squared, A times A plus 1. You get a positive thing under the square root. So you're going to get real eigenvalues. If A is less than negative 1, however, it's negative, and therefore A squared plus A will be less than A squared. Because that'll be positive, but that'll be negative. And the A out there is negative. You'll get a negative plus or minus some negative number, plus or minus some positive number, but that positive number will have an absolute value. I might say the absolute value of A will be bigger than the value of this. Try some examples if you are unclear about that. For example, if A is negative 2, let's just think of an example here. If A is negative 2, we get 4 minus 2 is 2 here. We've got a square root of 2 here, ultimately. We've got negative 2 plus or minus square root of 2. Negative 2 minus square root of 2 is definitely negative. Negative 2 plus square root of 2 is also negative. You're going to get two negative eigenvalues over here. Real and negative. And distinct, because if A is less than negative 1, you're going to get a non-zero number there. So the plus or minus has an effect. You'll get a sink, a real sink. So definitely a bifurcation occurs at negative 1. Those are your two bifurcation values, negative 1 and 0. I'm going to end this video at this point. I initially intended to make a longer video that would just be one, but it ended up being pretty long when I recorded it, about 41 minutes or so, and I didn't want any of my videos to be that long. So for this first part, I'm going to stop it right here. I never quite got in this first part to talking yet about that trace-determinant plane that I mentioned at the beginning of the video, and is the main topic of section 3.7. The rest of the video that I recorded this day will be separated as part 2 of this video, and in that part 2 I will definitely get into the trace-determinant plane for this example.